Welcome to this tutorial, where we explore the fundamental concepts of population and sampling in statistics. Refers to the entire group of individuals or items you're interested in studying. In the figure above, this is shown as a large group of people of different ages, including males, females and children, each one representing an individual member of the population. A sample is a smaller group selected from the population, meant to represent it. In the illustration, several smaller circles are shown with subsets of the population inside them. These are the samples, and each one includes a few individuals chosen from the larger population. This visual demonstrates how researchers often work. Instead of collecting data from every individual in the population, which can be costly or impractical, they collect data from samples and use that information to make inferences about the whole population. Statistics, population parameters are values that describe characteristics of the entire population. These are usually fixed but unknown because it's often impractical to measure the whole population. Here are some key population parameters. Population mean, denoted by mu, written as the Greek letter mu, represents the average of all values in the population. Population standard deviation, denoted by sigma, written as the Greek letter sigma, measures how spread out the values are. Population variance, denoted by sigma squared, is the square of the standard deviation and shows the average of the squared differences from the mean. In contrast, sample statistics are values calculated from a sample and are used to estimate the population parameters. Key sample statistics include: sample mean, denoted by x bar, written as x, is the average of the values in the sample. Sample standard deviation, denoted by s, measures the spread of sample values. Sample variance, denoted by s squared, is the variance within the sample. These sample statistics help infer the corresponding population parameters when direct measurement of the entire population isn't feasible. Sample statistics are used to infer population parameters through a process called statistical inference. Since it's often too difficult or impossible to measure every individual in a population, we collect data from a sample and use that data to make educated guesses about the entire population. Here's how it works. 1. Sampling. A representative sample is selected from the population. This sample should ideally reflect the diversity and structure of the population to avoid bias. 2. Calculating sample statistics. From the sample, we calculate statistics like x bar, the sample mean, s, the sample standard deviation, s squared, the sample variance. These serve as estimates for the unknown population values. Mu, population mean, sigma, population standard deviation, sigma squared, population variance. 3. Estimation. There are two main types of estimation: point estimation, using a single statistic, like x bar, to estimate a parameter, like mu. Interval estimation, using a range, called a confidence interval, within which the parameter is likely to fall. 4. Hypothesis testing. We use sample data to test assumptions or claims about population parameters. For example, we might test whether the population mean is equal to a certain value. Example: if you want to know the average height, mu, of all high school students in a city, you could select a random sample of 200 students. Calculate the sample mean height, x bar. Use x bar as an estimate for mu. Apply confidence intervals to express the uncertainty of your estimate. In short, sample statistics are like clues we use to uncover hidden truths about the full population, with tools like estimation, confidence intervals, and hypothesis tests helping us make informed decisions based on partial data. The goal of sampling is to obtain a representative sample, which acts as a miniature version of the population. This ensures that the insights drawn from the sample can reflect the larger group accurately. To achieve this, various sampling methods can be used, including simple random sampling, systematic sampling, stratified sampling, clustered sampling, or a combination of these methods. When these methods are used appropriately, they result in a probability sample, meaning each member of the population has a known chance of being selected. With a probability sample, valid conclusions can be drawn about the entire population based on the sample data. Simple random sampling is a basic and widely used sampling method where every member of the population has an equal chance of being selected. Key points. It is like throwing a fair die, completely random and fair. There is no bias in selection if done properly. It ensures that the sample is representative of the population, especially when the population is homogeneous. This method is ideal when you have a complete list of the population and want to ensure that your sample selection is purely by chance. Systematic sampling is a method where samples are selected at regular intervals from an ordered population. Steps. Select a picking interval, for example, every fifth item or person. This interval is usually calculated by dividing the total population size by the desired sample size. Randomly choose a starting point. One item is randomly selected from within the first group, e.g., one of the first 5. Pick every nth item, starting from the chosen point, select every fifth item, or whatever the interval is, throughout the population list. Example, if the interval is 5 and you randomly choose position 3 as your starting point, then you would pick individuals at positions 3, 8, 13, 18, and so on. This method is simple, efficient, and useful when the population is logically ordered and you want to ensure a spread-out sample across the list. Stratified sampling is a method where the population is divided into distinct subgroups, called strata, that share similar characteristics. Then, samples are taken from each stratum, either proportionally or equally, to ensure that all segments of the population are represented. Example, suppose the population is divided into age groups, 18 to 29, 30 to 49, 50 to 64, 65 and above. These age groups form the strata. Two common sampling approaches. Proportional allocation. The sample size from each group is based on its size in the population. For example, if 30% of the population is aged 30 to 49, then 30% of the sample will come from that group. Even allocation, equal allocation. The same number of individuals is selected from each group, regardless of their population size. This ensures equal representation across all strata. Stratified sampling is especially useful when there are important differences between subgroups, and it improves the accuracy and representativeness of the results. Cluster sampling is a method where the population is divided into natural or pre-existing groups, called clusters, such as schools, districts, or neighborhoods. Steps. Divide the population into clusters, for example, by schools or geographic areas. Randomly select some of the clusters. Not all clusters are included, only a few chosen at random. Draw samples from the selected clusters. This can be done by one-stage cluster sampling. Investigate all individuals within each chosen cluster. Two-stage cluster sampling. Taking a sample within each selected cluster using another method, like simple random or systematic sampling. Cluster sampling is especially useful when a complete population list is not available, but a list of groups, clusters, is, making it a practical and cost-effective sampling method. Non-probability sampling occurs when the sample is not selected randomly, meaning not every individual in the population has a known or equal chance of being included. Key points. It includes methods like convenience sampling, choosing those most easily accessible, self-selection, e.g., online polls or surveys where people choose to participate, and street interviews. These methods are often quick, easy, and inexpensive, but they introduce bias. Since the sample may not represent the population accurately, you should avoid making general conclusions about the entire population based on non-probability samples. Non-probability sampling is useful for exploratory research, pilot studies, or when probability sampling isn't feasible.